Good evening, everyone. This is JEE Advanced lecture number 6, and we are dealing with magnetic effects of current. Yes or no?
Yes, sir.
In the last class, we had seen magnetic field, and in this class, we will also see magnetic force and try to solve some good problems in JEE Advanced. Now, before going into that, let me just bring to you this thing into the picture, whether you know this or not. You may not have seen this. So, if you want, you can note this thing down. You might not find this, you might not have gone through this. So, notice down, this is a combination of what I call magnetism and modern physics. So, some things related to magnetism as well as modern physics. I can call it by the heading of atomic magnetism. Now, you know the Bohr's postulate in modern physics, yes or no?
Yes, sir.
The first the postulate is this: the angular momentum mvr is nh by 2 pi. Number one, yes or no? Then, if you have any electron moving in Bohr's orbit, the centripetal force must be provided by the attraction force between the positively charged nucleus and the electron, yes or no?
Yes, sir.
These are the two things that you must remember. Now, sometimes there could be a question in JEE where they mix modern physics with magnetism, and they ask you what is the orbital current in the second shell, first shell, third shell, and so on. I have not seen a problem come till now, maybe once or twice it has come, but it's very simple to understand. How do you find the value of orbital current? The orbital current will be given by this formula. Yes or no? Do you understand this? Q or E, the charge on electron divided by the time period, and time period can be written as 2 pi by omega. So it becomes like this, where omega is the angular velocity in the given orbit. Yes or no?
Yes, sir.
This will be the orbital current, the current that the electron produces when it is revolving in this orbit. Now, because of this current, this electron will create a magnetic field at the nucleus. Now, just note down this. It is very simple to deduce it, but if you know it, this field can be found out by this formula: mu naught I by 2r, where r is the orbital radius and I is the orbital current. If you put these values, you will get the magnetic field created due to orbital current will be mu naught E omega or Q omega by 4 pi r. Do you understand this?
Yes, sir.
So I'll request you to note this down. You can note this down. I'll give you 2 minutes so that you can note this down. Well then, we have found out the orbital current. We have also found out the magnetic field due to orbital current. The next thing they would ask is the magnetic moment when this electron is rotating in a circular orbit. Remember, it is I multiplied by, I told you that, right? Magnetic moment of a current carrying coil. So this is just like magnetic moment of a current carrying coil. You know the orbital current multiplied by the orbital area, and this is how the formula would look like. Just have to put the value of omega and orbital radius. Then they could ask you whether it is directly proportional to z or inversely proportional to n number of electrons, whatever. Once you know this formula, and once you know the basic formula for orbital radius, omega and v, I'm sure you know it. If you don't worry. After this, we will go to modern physics and we will go through those formulae. So that is how questions are framed, and they will ask you if the orbital angular momentum or magnetic moment of an electron in hydrogen is this much, then what will be the value for helium or lithium or any hydrogen like atom? Questions are pretty simple. Now, one very important concept here, which I would like you to remember, is the relation between the magnetic moment and the angular momentum of an orbital electron. I'm not sure whether you have noted this down or not, whether you know this or not. Remember, this is the relation. Magnetic moment vector wise is minus E. Remember, charge of an electron is minus E into L vector by 2m, where L vector is the angular momentum vector. Have you seen this formula? That means magnetic moment and L vector are anti-parallel axial vectors if we are talking about angular momentum for orbital electron, or the relation between magnetic moment and angular momentum for an orbital electron. Please note it down. I don't know whether you know this or not. Please note it down. Okay, then we move ahead, and again, angular momentum MVR for a Bohr's orbit is nh by 2 pi, and now that I know the relation between magnetic moment and angular momentum, so you can have this formula for magnetic moment as well. If I put the value of n as 1, the first orbit, this m becomes this one. This is known as Bohr magneton. Might not have heard this term. No one is going to ask what is a Bohr's magneton, but just remember that since you know the relation between m and L, and you know L is nh by 2 pi, this is how they correlate things in a JEE. You should know the relation between m and the principal quantum number n. Do you understand this, bacha? M and principal quantum number n. Okay, so just remember this. Everything else is a constant. E is a constant, h is a constant, 4 pi is a constant, m is a constant. The only variable is is n. So magnetic moment is directly proportional to n. Please note this. I'll give you a minute to note this down. So let me move ahead and come to the point where probably you would have heard about this. If you have a charged body, now this charged body could be a ring, this charged body could be a cylinder, solid cylinder, hollow cylinder, this could be a sphere, this could be a disk. If it is rotating with a constant angular velocity, it will behave as a current carrying loop, and then it will create magnetic field as well as it will have magnetic moment. And the relation between magnetic moment of this body, solid body, and L is m by L is q by 2m. In fact, they have the same direction as well. If it is positively charged, m and L will be in the same direction. But if the body is negatively charged, as in the case of an electron, the direction of m and L would be opposite. Do you know this formula, beta? M by L is q by 2m. Yes or no?
Yes, sir.
Okay. So remember, this formula is valid for all solid bodies which are rotating. Now remember, apart from remembering this one, you must remember that this rotating body is also like current, and you can easily find the current which this body is producing. Yes or no? For example, if a ring of radius r and charge q is rotating with an angular velocity omega, what will be the current, bacha? What will be the equivalent current? Just take this example. What will be the equivalent current? Mm-mm. The equivalent current will be q divided by t, which is 2 pi by omega. Yes or no, bacha? This is how we found out the orbital current for an electron. Yes or no? Now remember, and mark it as very, very important concept. Now they could ask you, what is the magnetic field created at the center of this loop or the center of this ring? Now, how do you do this? Remember, you know that this ring is acting like a current carrying wire. So now it's a circular current carrying wire, and you know the formula for magnetic field at the center of the loop, and the formula for magnetic field at the center of the loop is how much? B at the center of a loop of a current carrying wire, mu naught I by
Not by 4
2r. Yes
by
or
R.
no?
Yes, sir.
You just put the value of I from the above equation and you will get your results for this. Are you getting my point, bacha?
Yes, sir.
Now, how can they make a difficult question? Now, instead of a ring, they will now get it into a what? They'll make it a disk of radius r and having total charge q is rotating with an angular velocity omega. The first question they could ask you is what is the magnetic moment of that disk? That is very simple because m by l is q by 2m. Yes or no? You know the angular momentum of this. This is I into omega. Angular momentum is I into omega and I is mr squared by 2. Yes or no?
Yes, sir.
You can easily calculate the magnetic moment of this. But if they ask you what is the magnetic field at the center of this disk, what will you do? Are you getting my question, bacha? You will not find this question anywhere in the books. You realize the question that I made?
Yes, sir.
A disk of radius r, mass m, charge q, radius r, mass m, charge q is rotating with a constant angular velocity omega. What is the magnetic field at the center of the disk? I'll give you 2 minutes. Think about it. Okay. So, how to do this question if it comes? So, this is a disk. Now, to get it into a disk, I would put this like this so that you understand that it is now a disk. Okay. Oops. It is now a disk. Okay. Now it is rotating. Let us say like this with a constant angular velocity omega. The mass of disk is m and the total charge is q. Have you done this? Yes. So how do you do it? In short, what will you do? You will convert it into small rings. Are you getting my point? You will convert it into small rings. This small ring has a charge dq. How much is that dq? That dq will be equal to 2 pi r dr. Yes or no? That small disk will have small charge 2 pi r dr. That is the area multiplied by q divided by pi capital R square. Yes or no? Now you divide this dq by 2 pi by omega, you will get the current. Now, once you get the current, this current would be your di. Yes or no? Now, with this di, you can calculate the small magnetic field dB. That will be equal to mu naught di by 2r. Yes or no? And then you integrate because all these fields will be in the same direction. You integrate it from 0 to capital R and you will get the magnetic field at the center of the disk. Yes or no? Is it the same thing? So once you have this concept, you can solve all these questions. I would be having these answers, standard answers somewhere. I will find out if I get this answer and I tell it to you. Magnetic field at the center of a rotating ring, magnetic field at the center of a rotating disk, magnetic field at the center of a hollow sphere, magnetic field at the center of a solid sphere, and so on. Magnetic field at the center of a rotating cone and all that. I don't think they will ask this, but the most difficult question they could probably ask here is a ring and a disk. They might not ask you more than that. So, do you understand how it is to be done? Okay. So remember this. because this might come in handy if they frame a question on this. This is how the question will turn up. Having said that, this is a small table that I have with me, where the magnetic moments and the magnetic moment and moment of inertia are written, and you see the relation is same. Do you understand this? For a ring, for a disc, for a solid sphere, for a spherical shell, these are the magnetic, these are the moment of inertia, and these are the magnetic moments. Got my point? So they have the same thing coming up. They are in the same ratio. M by L is Q by 2m. Now let us quickly move on to force on a moving charge, and I must tell you that it is given by QV cross B. Yes or no? You know this is a cross product of V and B. Since it is the cross product of V and B, this force is perpendicular to V, as well as this force is perpendicular to B. It is perpendicular to both V and B. Since it is perpendicular to both V and B, the power or the work done by this force is always zero. Yes or no? You understand this? Work done by magnetic force is always zero. That means this magnetic force cannot change the kinetic energy of the body. It cannot change the kinetic energy of the body. It means that it cannot change the speed of the body. Then what it can do, it can only change the direction of velocity of a moving body. And that too only when the body is moving. If the body is at rest, it cannot start the motion. If the body is moving, it cannot stop the motion. It cannot change the magnitude of speed. It can only change the magnitude. No, it can only change the direction of velocity. And that too it can only do when the particle is moving and the angle between V and B is not equal to 0 degrees. Do we realize this? Yes or no? We know all these points. If we know all these points, then we can move on to what type of motion a particle will have if it is put in a magnetic field. Now, this motion can be put into three categories. The first category is angle between V and B is 0 or 180 degrees. In that case, nothing will happen. The particle will go undeviated. Yes or no? The second case is where V and B ka angle is 90 degrees. In that case, the speed in any case will remain constant. In this case, the particle is moving. If it put in a magnetic field, it will always move in uniform circular motion. The radius of that uniform circular motion is mv by qb. You must be knowing this. It is given here as well. Yes or no? It will rotate with a constant angular velocity omega and a constant frequency. That frequency is also known as the cyclotron frequency. You must have heard about it. Yes or no? Okay, so that is case number one or case number two, depending on where you are looking at it. Now, the third case would be when the angle between V and B is not 0 or 90, it is somewhere between 0 and 90 like this. Then what can happen is I can resolve this velocity V into two components. One is along the magnetic field and one is perpendicular to the magnetic field. The perpendicular component, because of this perpendicular component, it will move in a circle. Because of this parallel component, which will not change, the particle will move ahead. So the particle will move ahead and it will also move in a circle. The motion of the path, the motion of the particle will be a helix. And you know the time period of this helix, yes or no? And you also know the pitch, the distance traveled in the horizontal direction in one rotation. You must be knowing this, helical screws. All these things would be known to you. Let us not waste time there. Now, problem will come only when you have both the things combined. When I say both the things combined, that means you will have electric field as well as magnetic field, and a particle is subjected to electromagnetic force. Then we use this Lorentz force ka formula, Q into E plus Q V cross B. Yes or no? Okay. If magnetic field is present and electric field is absent, this is a motion in a magnetic field. If magnetic field is absent, electric field is present, this is motion in electric field. If both are present, then it is a motion in electromagnetic field. Now we can understand this motion under various heading. The first heading is V, E and B all are collinear. What do I mean when I say collinear? V, B and E all are in the same direction. Then what type of motion the particle will have? So we will be studying them into separate headings. So that's how the things will become simple. I'll give you 2 minutes. Tell me what will happen if V, E, and B all are in the same direction. Well, this case is very simple. If V, E, and B all are in the same direction, B magnetic field will not be able to do anything because of electric field. If it is a positively charged particle, its speed will keep on increasing. If it is a negatively charged particle, its speed will first decrease, it will become zero, and then it will turn back. So the motion would be motion in a straight line. Do we understand this? Yes or no? Okay. Now we can have a case where E and B are parallel and particle has a velocity which is perpendicular to both E and B. Then what will happen? Do you understand the scenario? Do you understand the scenario? Okay. So can you tell me what will happen if I'll try to make it. I hope you can see this. If you have a scenario like this, where E and B are in the same direction and V is perpendicular to this, what type of motion the particle will have here in this case? Case number 2. So this will be because of electric field, its velocity along x-axis will keep on increasing. Electric field cannot change the other velocity because electric field is along x-axis. But because of initial velocity along y-axis and magnetic field along x-axis, it will rotate in a circle. Yes or no? So it will rotate in circles and it will move faster along x-axis. So the path will be helix or helical with increasing pitch. Do we understand this? The pitch will keep on increasing and it will follow a helical path. Yes or no? Okay. Now the third case will come, and which is a very peculiar case. Now the third case, in the third case, what can happen in one of the particular scenarios that V, E and B both are perpendicular to each other. V, E and B, and in most of the cases you might get this particular case. E, V and B are perpendicular, and in such a way that the electric force and the magnetic force, they are in the opposite direction and they get cancelled out. In this case, the velocity will be E by B and the motion of the particle will be motion in a straight line. Do we understand this? This is a very peculiar case. This is a very peculiar case, and this might be the case which might come into exam. So please note it down. I'll give you 2 minutes to do it. So now let us move on to a simple question. In this simple question, The particle is moving in a uniform magnetic field. The region between x equal to 0 and x equal to L is filled with a uniform steady magnetic field B is equal to P naught K. A particle of mass m charge Q velocity V enters velocity P naught I. Neglect the gravity. Gravity is not there in such a question. You have to tell me, find the value of L. The particle emerges with its final velocity, taking an angle of 30 degrees with the initial velocity. Can you do this? Have you done a question like this before? Now remember, whenever a question comes and a particle is put in like a magnetic field and the angle is 90 degrees, remember, forget about everything that you know. Remember, this is a very simple question of uniform circular motion. You understand? Whenever V and V are perpendicular and a body is protected, no matter which question, the magnetic, remember it is not a question of magnetic field, not a question of force, very simple question of form. But you understand this? Having said that, uh, remember this question has two parts. First part they want to ask for what value of L particle emerges, final velocity. Second part, find the velocity of the particle and the time spent by the particle in the magnetic field now extends 0.1 times due to. So how this question has to be done? Remember, it's a simple question of uniform circular motion. Whenever whenever such a question comes, just have to see where the particle is entering, where is the center, and how it is being placed. If I assume that the particle enters here, you can find out P cross P. You can find out the center of the circle will lie somewhere here. Yes or no? To know that the radius of this circle is r, which is mp by qb. Now it is a simple question of uniform circular motion. With this center, this particle will move. This angle is 30 degrees. To know the radius of this arc is mp by q. Then it is simple plane trigonometry. This angle is 30 degrees. So this angle is 30 degrees. This is r. This is l. Can calculate the relation r and l. Yes or no, bacha? Got this? Remember, this is a simple question of what? Simple question of uniform circular motion. And in the second case, when you have L becoming 2.1 times L, so L becomes greater than 2R, will get it like this and it will be able to move in a complete semicircle and it will come out after spending half of the time period. You can understand this, bacha? Any question that comes this pattern have to be solved like this. I will give you one more so that I'm confident that you can do questions of this nature. One more. And this is the one, and I want the answer quickly from your side. This is how the electron or charge particle is entering. This side we don't have any magnetic field. On this side you have magnetic field which is going inside. A positive charge of charge 2 mass m enters into a uniform magnetic velocity. There is no magnetic the left of you 5 times 10 distance travel impulse of magnetic force. That means they are asking us the change in linear momentum. Do we understand this? Apart from this, there could be many more questions that we can ask. For example, they can ask that if this is the origin, at which point it makes the exit. telling the coordinates of that point. Can also ask you what is the maximum x coordinate. Remember, it is simple geometry. Simple geometry. Once you understand that this question, the question of PM is simple geometry. I finish all this one. So, but as I told you, this is a straightforward question. Once you realize that the particle is actually here, to do V cross B, you find out the center of the circle, then you just rotate it in a circle. Whatever angle it enters, it the same angle it will come out. Whatever speed it enters, the same speed will come out. The direction will be reversed. You know the center of the circle. You know this radius. Then you know the constant angular velocity omega. Omega into theta is omega into t is theta. So from there you can find out the value of the angle t. Yes or time t. Yes or no? Then they ask you distance travel. So distance travel is length of the arc. R multiplied by 2 theta. You have to find out the impulse. Impulse is nothing but change in momentum. Initial momentum minus final momentum minus initial momentum. Got all these answers correct? Yes or no? Got all these answers correct? Remember, there could be a combination coming from this question, and let us now move on to a different question. And I hope that we could be able to this as well. This question may entice you. Remember, no question is tough. Only a perception of the question that makes it your tough. Here it comes. The next one, a charged sphere of mass m and charge 2 starts sliding from rest. Not a question of pulling. Charge sliding from rest on a vertical fixed circular track of radius r from the position s shown in figure. There exists a uniform, constant, horizontal magnetic field of induction. Find the maximum force exerted by the track on the sphere. Ready? Magnetic point. So it is not horizontal. It would be if you look at this diagram, the dot is given. You understand the meaning of dot? So I mean they have given the side view of this diagram. Okay, beta, you understand? So it is coming out. Okay. Okay. So I'll give you 2 minutes. Think about this. Okay. Here this all. We just have to find out take any angle theta and draw the FPD of this body. It is going down. Yes or no? mg cos theta and sin theta depending on whether you have taken from the horizontal or vertical. We have taken the angle horizontal, therefore mg sin theta is here and mg cos theta is the other side of the magnetic. So, and then you have normal reaction and just have to find out if direction is the uh, magnetic force acting. P is like here, B cross B you got to so B cross B, and in which direction it is pointing this magnetic force. B, B is along the track. B in the horizontal direction. So B cross B will be coming outward. Yes or no? The magnetic field, magnetic force pointing the outward direction. Then you just draw the free body diagram. N minus mg sin theta minus dp will be mv squared by r. N will be equal to mv square by r plus mg sin theta plus e. Yes or no? Then where do you have the maximum value? Remember, it depends on 3 things. It depends on b, it depends on theta, and it depends on b again. So it will be maximum where b and theta and sin theta are maximum. Yes or no? So there is only one place possible. B, when it reaches the lowest part, you can find out the value of that B root over 2gr. Yes or no? Just put those values here and you have answer. Remember, that is why this magnetic field was put in this way, because if the magnetic field would have been the other way, sine theta would have got subtracted and that would have created a lot of problems. Getting my point, bacha? So, this is how this question was framed. Remember, there are some questions which are framed in a particular way, because frame it in a different way, then the question, which might be very simple, it might become a little troublesome. I think you might have seen this question before. An electronic gun, G, emits electron of energy 2 kilo electron volt traveling in the positive direction. The electrons are required to hit the spot S. The GS is 0.1 meter and the line GS makes an angle of 60 degrees with the x-axis as shown in the figure. The uniform magnetic field B parallel to GS exists in the region outside the electronic gun. Find the minimum value of B, make the electron hit S. So how are you supposed to do this? First of all, you can find the velocity of electron. The energy is given, kinetic energy. That energy is kinetic energy. Find the velocity of that electron. Now, this velocity of electron can be resolved into component V cos and V sin. Because of this V cos theta is moving along the axis. Because of V sin theta, it is moving perpendicular. It has to strike that gun at that spot. That means it will strike, it will come on the axis in one time period. One time period, if it hits, it will strike it. Now this electron can hit either after one time period or after time period or after three time period, but on the minimum value of B. Minimum value of B will only be achieved when it hits in the first time period. Yes or no? The distance traveled along the axis will be V cos theta multiplied by T, and that is very simple. Yes or no? Okay, I think this question was taken from S.C. Verma. That is what I can stand out for. Now, let us move to this part, technical part, we have already seen. Let me ask you this question. And I would suggest you must be having S.C. Verma with you. So I would suggest that there are questions of S.C. Verma multiple choice question that would be good, because there might be a question of which of the following combination of E and B is possible? There are 6 or 7 or 8 or 10 questions of the same nature. Solve them. Which of the following combination of E and B is possible if a charged particle passes undeviated from a region? So, don't want the particle to get deviated. Which of the following combinations are possible? Multiple choice question. Remember, this is how questions are framed in the JEE. What all combinations are possible? Remember, 8 or 10 questions are given in SQ Verma multiple choice, analytical current. You can solve what 8 or 10 or 2. If a question comes in multiple choice, it comes for what is the answer for this one? A, B, C, D. Which combinations are possible? So that the particle goes and give it 2 minutes. Think about it. Okay, and that is the correct answer. 1, 4. All the options are possible for a particle to pass undeviated. You understand this? I hope you have got the correct answers. You understand the logic behind it. Second question is a part of the first question. In the above question, charge particle passes undeviated without changing its velocity. That means without changing speed, I think. The above question, the charge particle passes undeviated without changing velocity. Uh, that means it can change its speed, but it cannot change its direction. I think that the question is same whether I ask it like this or I ask it like that. Okay. So as I told you, SCV many questions of this nature are given. So that would be my request. You can solve those questions on your own. Can you do this? The answer to this one is also 1, 2, 3, 4. Yes or no? Nothing has changed. Okay. Got it? Shall I move forward? Okay. Now, remember the case where I talked about E and B are perpendicular, E and B are parallel, and then you project a body. What will be the motion like? Now, I found out the entire analysis, the note. So, remember, you can just note it down because there could be a direct question out of this. E and B, as you can see, are parallel, and I project a body, very general case at an angle theta. What happens to this body? Remember, this is my x-axis, my y-axis, and this is my z-axis. So the velocity of one component is along y-axis, the velocity of other component is along x-axis. This component is going to change because of the electric field. It will become more and more. Because of this component, the particle will move in a circle, and this will be a motion, the helical path with increasing pitch. Yes or no? So in x direction, force is QE, acceleration is P by M, initial velocity is V naught cos theta. So you can get the value of x as a function of time. This is x coordinate of the particle as a function of time. Velocity along x will be equal to V naught cos theta plus ax into t. So we know everything. We know the velocity along x and we know the position along x. Please note it down. This is a complete analysis of case where E and B are parallel and you project the velocity. Have you noted it down? And you can also note what happens in the yc state where the particle is moving. The radius of the circular path will be given by mp perpendicular by qt. The angular velocity will be given by this. Now you can find out the x coordinate we have already found out. You can find out the y and the z component, and you can also find the velocity of y and z component. You can understand this? So to have note, this is the final result that you are going to get. The radius vector r of a particle along I, along j, and along k will be like this. The velocity vector will be like this. The acceleration vector will be like this. If you remember any one of these, you can understand the other two by simple integration or simple difference. Understand this? Okay. So this was the analysis on this one. Now, when come to some examples where you might have combined electric and magnetic field, or some question in which magnetic field is varying, as the first question that comes. Yes, you might have seen this question. But again, a long straight wire carries a current. Question has come in JEE also. Right. A particle having a positive charge Q and mass m, kept at a distance x naught from the wire, is projected towards it with the speed v. Find the minimum separation between the wire and the particle. Have you seen this question? Yes or no? The time that you solve it. I'll give you 2 minutes. The only difference between this question and the previous question, where the previous question magnetic field was uniform, now the magnetic field is not uniform. That is the only difference. The magnetic field is uniform, it is UCM, circular motion, uniform circular. But if the magnetic field varies, it is no longer UCM. Think about it. Give you 2 minutes. So the question was this, that we have an infinite long wire and we have a particle thrown towards it at a distance of x naught. If you can just draw the free body the diagram, this is how the diagram looks like, and I have thrown it, projected it with a velocity v naught. Now, when will be the separation between this wire and the particle minimum? When its velocity becomes completely vertical? Yes or no? That's it. Force on the body will be QV cross B. Now remember, magnetic field is along Z axis, minus Z axis here. The particle will move in the XY plane. We know this because velocity is in the XY plane. Magnetic field is along the Z axis, minus Z axis. It has to move. So I can write this velocity like this. Even if you write the Z component, when you cross it with this Z, with this K component, it will become zero. So doesn't matter. Even if you write velocity at Vxi, Vyj, and Vzk, K component will get cancelled. Once you find out the force, force will be having two components, one along J and one along I. Yes or no? So you have two accelerations, one acceleration along the x-axis and the other acceleration along the y-axis. Then these accelerations are in terms of Vy and Vx. Do you see this? You will get this acceleration in terms of Vy and Vx. You can see there acceleration x is fx by m. You can just substitute everything here is a constant. So I can just substitute it as lambda. But lambda is this thing so that the question becomes simpler. Now this ax can be written as Vx into dv by dx. I also know that Vx square plus Vy square is V square, that is a constant. So from here you can find out relation between V dx, which is here, and V dy. So I'll put this V dy here, and the equation number 1 now starts to look like this. Vy dvy by dx is lambda times Vy by dx. Are you following me, bacha? What is happening here? Now you just have to integrate it. If you just integrate it, you will be landing with the result that is required. You know the limits in terms of Vy. Initial velocity along Vy was 0. You want it pointing downwards, minus V. Initial distance along x-axis is x naught. And you will get this as this one. I'll give you 2 minutes to note this down. We move on to this question where you have an electron is released from the origin at a place where a uniform magnetic field E and uniform magnetic field exists along negative y-axis. So electric field is along negative y-axis and magnetic field is along negative z-axis. Find the displacement of the electron along the y-axis when its velocity becomes perpendicular to the electric field for the first time. So what is going to happen is because of the electric field, the speed is going to change. Because of magnetic field, the direction of velocity is going to change. So at some point in time, we'll come to a point where its velocity will become perpendicular to the electric field, because starting May, the velocity will be pointing downwards, will keep on increasing in the downward direction because electric field is pointing in the downward direction. But because of magnetic field, it will try to rotate it in the xy plane. Therefore, the direction of velocity will keep on changing. You have to find out the time where the velocity becomes perpendicular for the first time. I'll give you 2 minutes to think about this, and I'll give you the result, and you remember that result. So if you have to solve this question, you have to remember that this is going to follow the path of a cycloid, and you have to remember how it is to be done. Now remember, this particle is going to move along x-axis and y-axis. X-axis and y-axis. So we use the Lorentz force equation. This particle will move in the xy plane. So I write the velocity as uxi plus uyj. Electric field is along minus y-axis. Magnetic field is along minus z-axis. I find the Lorentz force. It is a electron. So I multiply it by minus e. This is the Lorentz force that I get. If I look at the x component has velocity along y. If I look at the y component, this y component has velocity along x, and that is the problem to solve this question. So once I get the value of velocity, You can divide this velocity. Once I get the forces, I can divide these forces by mass, and I will get the acceleration along the two axes. Acceleration along x will be QE by or EB by m into UY. Acceleration along y will be E by m into E minus UB into x. To solve this, there are different ways of solving this. The easiest way is to find the double derivative of acceleration of y. In this double derivative of acceleration of y, you will find the acceleration of ax, and you can substitute the acceleration of ax, and you will get the double derivative of uy as minus omega square times uy, where omega is equal to E by m. So this now becomes equation of SHM. SHM not in terms of x, but SHM in terms of u. But more doesn't matter, u or x, u or an x, both are functions of x or y. Whatever happens, you get the value of SHM, and this is how you can imagine that the SHM is like you can write uy as a sine omega t plus delta. Then you can find dy by dt and just put the values. So uy, the velocity along y, will be looking like this. And if you want to find out at what time the velocity will be perpendicular to E, uy component will become 0. From there, you will get the value of time. You put the value of time in the equation for y, you will get the position where the particle becomes perpendicular to electric field. Remember the value of uy and y. This is what is important. And the value of omega. You can remember these. Value of y, omega. I think you should be able to solve this problem if it ever comes. In a JEE, remember, they might not ask you to solve this because it is too much to do in an examination hall. Remember that it is a cycloidal path. That would be good enough. And the force on a small element of a current carrying wire of length dl is I dl cross B. I hope you know this. It is very simple. And if you have a wire, a loop of wire placed in a uniform magnetic field for any shape, for example, if you have this closed loop of wire and it is placed in a uniform magnetic field B, the net force acting on this wire will always come out to be 0. Do you know this, beta? You know this? Yes or no? Okay, if you know this, that means if you have any random shape of wire which is placed in a magnetic field and someone asks you what is the force on this, what you got to do is just close this wire, find the force on this segment, and the opposite of that would be the force on the loop of wire acting. I hope you know this. Before winding of this class, I'll just ask you to solve this question. Remember, the only thing that is different in this question is that instead of wire being placed in a uniform magnetic field, wire is placed in a non-uniform magnetic field. A question of this nature has come in JEE sometimes back. So I'll request you to solve this. I'll give you 2 minutes to do this. The question is pretty simple. I have two infinite wires, I1 and I2, and you have a small element dl of the wire. They're asking you to find out the force between the two wires. I think you can do it. That's or no? Okay, I'll give you 2 minutes to solve it. I I think you would have solved this question. It is pretty simple. You just have to find magnetic field at a distance of L, or at a distance of x is mu naught I by 2 pi x. Then the length of the wire is given as dl. Angle between B and dl is 90 degrees. This will be the force acting on this small wire. We have started with the magnetic force on a wire. Okay, and the next class we will be doing some problems on this magnetic field, magnetic force on wire, and also some more problems. So combine everything we have covered now. In the next class, what we will do is we will solve all the questions put together, and then if we are done with this, then we will start with EMI. Okay, if you have any doubts, you can ask me. Okay, so we have covered all types of questions that could be asked on force on a charge, force on a wire. We have not done. I've told you that if it is a uniform, if it is a closed loop placed in a uniform magnetic field, the force would be zero. But now we'll have to solve questions where it is not placed in a uniform magnetic field, right? So we will do those questions. Force on a wire in a non-uniform field, force on a loop on a non-uniform field, and then we will solve some typical questions as well. The sort of question that can come in a JEE. That will be done in the next class. I'll try to cover each type of question that can come in this category. That will take some time. Maybe around 8 or 10 questions. If we do, we will be covering up almost all types of questions. And then if we are left with time, we will start with the next topic, that is EMI. If you have any doubts, you can ask me. Okay. So I'll meet you tomorrow. Take care. Have a nice day.